Hi class, back again talking about some more applications to physics that our integral can help us with. This one's going to be about hydrostatic pressure and force. So what we're trying to think about here is the amount of pressure applied to a horizontal plate that's submerged under some kind of liquid, whether that be water or any other kind of liquid. And what we mean by that is how much pressure due to gravity does anything submerged in water feel as all of the mass and gravity of that water presses down upon it. So again, I encourage you to pause the video as necessary to take notes, and you're also going to need the handout that is on Blackboard to follow along with these problems. So we're going to start talking about hydrostatic pressure and force with a nice rectangular prism of a tank here. So if you look at your handout and number 1, it says that we have a tank that is 8 meters long, 4 meters wide, and 2 meters high. It's full of kerosene, which has a density of 820 kilograms per meter cubed, and it's filled to a depth of 1.5 meters. So let's take a look at that. I've got a tank here, 8 meters long, 2 meters high, and this is 4 meters wide. Now take a note at how I labeled my x-axis this time. This time allowing my x-axis down here to be at the bottom of my tank, moving up, because my tank isn't all the way full. So it may be easier for me later on to take the height of the kerosene at 1.5, the height at the top of the tank of 2. Now I'm not trying to move any of this out of the tank this time. I'm going to be calculating different things. I want to know what it feels like to be a plate on the bottom of this tank. So the first part asks us to find the pressure at the bottom of the tank, or what kind of pressure is the bottom surface feeling. So let's take a look at that. Here's the bottom of our tank. And it's going to be feeling some pressure as all the kerosene on top of it is pressing down on it. So we're going to need to understand a little bit of basic physics to answer this question. So let's look here at pressure. Pressure is defined as the force per unit area. And so we want to talk about force, and that's going to be the force of the kerosene pressing along the bottom of the tank, which is going to be a rectangular horizontal plate here. So that's the force divided by the area. So in order for us to find force, we need this guy rho here. The Greek letter rho, it looks like a lowercase p, but it's not. Gravity times the area and the distance of water, in this case kerosene, pressing down upon it, divided by the area. So here we have the density, the gravity, and the depth. Now depending on the units that we're working in, and this one is kilograms, we're going to need to include gravity because this density is the mass density. But if we were to be working in feet and pounds, then we could use this form. This is delta, but it is just the force that already includes the force of gravity, like the unit pound does, whereas the unit kilogram does not. So either one of these will work, but for this particular problem, since we're working in meters, we'll use this form here. So in part A, we're asked to calculate the pressure just at the bottom of the tank. So to do that, we're going to basically have no variation. All of the water is pressing down upon that bottom. So we just need to plug into our pressure formula. So since we're working in kilograms, we'll work with this pressure formula here, rho g d, and plug in what we know. So in the problem, it tells us that the mass density of kerosene is 820 kilograms per meter cubed. We know the force of gravity is 9.8 meters per second squared. And now let's talk about the depth. So we want to think about how much water is pressing down on this plate. And this tank isn't completely full. So the amount of pressure, the amount of kerosene that's actually pressing along the bottom of the tank has a depth only of 1.5. Since I named this to be 0, I have 1.5 meters of kerosene pressing down on the bottom. So this is a simpler calculation because nothing is changing. This is a constant pressure pressing down upon it. So the pressure at the bottom of the tank, when I multiply all of those together, is going to be 12,054 kilopascals or newtons per meter, whichever unit you like. Okay, so that wasn't too interesting, but let's see if we can calculate the force that the water is the force of the weight of the water at the bottom, and then we'll see what happens if we try and calculate the force where something is varying. So let's look at this definition over here, the force of water on a horizontal plate. You can see actually it's built in over here, force per unit area of the pressure problem, and we just include back in the area of the plate. So here we have force equals the density times the gravity times the surface area of the plate times the depth of the plate in the liquid. A is the area of the plate, and D is the depth. So again, nothing is changing here. Our plate is not varying, so we should be able, in part B, to calculate kind of easily the force at the bottom. So using this formula over here, I was given that the mass density of kerosene is 820 kilograms per meter cubed. I also know the force of gravity is 9.8 meters per second squared. And now let's talk about the area. Well, the bottom of the plate, the plate at the bottom is a rectangle, and so we should be able to just use these dimensions to compute the area of our horizontal plate. So that should be 8 meters, length times width times 4 meters. So our area should be 32 meters squared. Just the area at the bottom. One last thing, how much kerosene is pressing down on our plate? Well, 1.5 meters of kerosene is pressing down on our plate. And so that should give us the force at the bottom. So if we put all of those values together, we get about 385,700 newtons. And we could say that's about 3.86 times 10 to the 5 newtons of force acting on the bottom of the tank. So what's not very interesting about the bottom of a tank or the pressure along the bottom of a tank is that nothing is varying. It's a very straightforward calculation. What might be more interesting to look at is what's happening at the edge of a plate. So let's say we were talking about the pressure at one end of the plate. Well, that's not constant because gravity and distance change, and so the force at each kind of individual level here is going to be different because the force is higher the deeper you go. And so you can imagine that if we were to take a similar construct that we've been using all along and look at a slice, we might be able to add up all of the slices using a Riemann sum and get to what we're actually looking at. So let's look at that in Part C. Part C asks us to find the hydrostatic force at one end of the tank. So let's see if we can do that. Might need a little bit more work to do so, but I think we can get it done. Okay, so first of all, let's take a look at one slice of one end of the tank. I'm going to get rid of this bottom because we're not looking at the bottom anymore. And instead, let's just look at one mini little plate here. Okay. And let's see if we can figure out some information about him, and then we might be able to sum up some other things there and get ourselves going. So in order for us to build up pressure or force, we're going to need to know the surface area of our little thin vertical plate, and we're going to need to include some things about density and gravity and depth to that little plate. So let's talk about this little plate. I know that the length of this plate is 4 meters, and perhaps I'll choose some delta x to be the width of my plate. So for one vertical slice of a plate, we'll get the following information. So the area, just on this one slice here, is going to be the length times the width, which is 4 meters times delta x meters, or our area is just 4 delta x meters squared. Because I'm going to take some small little plate, and eventually I'm going to let that delta x get so small that I have infinitely many of them in there. We're also going to need to know the pressure on that one little plate, so let's talk about that. The pressure is just going to be rho times g times d, the density times the gravity times the depth. So let's go ahead and see what that looks like on our diagram here. So if I choose some xi here to represent the location of my disk, then I can probably set up an equation to figure out the pressure at that disk. So I was given that kerosene has a mass density of 820 kilograms per meter cubed. Gravity, we know, is 9.8 meters per second squared. And this guy, this plate, happens to be at a depth of xi meters. So putting that all together, the pressure at my individual single slice of a plate is 820 times 9.8 times xi. So let's put those two pieces together to get the hydrostatic force just on that one little plate, and then you can imagine that we can build it up and we can get it going. So if I quickly do force, I just need the area times the pressure for each individual slice. So we just said the area was 4 delta x meters squared. And we just said the pressure was all of this business over here. I'm running out of room, so I'm just going to erase this really quick because I'm going to put the xi meters here. And now if I just remove my units for ease of operation and multiply together my constants, can I do that in my head? I don't think so. I will get 32,144 delta x newtons, working just on that individual slice of a plate. So now we're going to apply our Riemann idea to this slice, and we're going to see if we can figure out the force on each individual slice coming up that side of this tank, and that the slices get so thin that we have infinitely many, so that we actually get the full hydrostatic force at one side of this tank. So let's do that next. All right, so this is for one slice. How could we figure out the force on all of the slices? Well, as I mentioned, we could take infinitely many slices, and we could add up the force at each one of those, and we should end up with the total force as we get from the bottom to the top. So if we do that, we're going to be using each individual guy here. Oh, did you notice I left off xi on here? If not, now you did. And that's important because I'm actually going to do a little bit of rearranging and put the xi here, and then my delta x there. Now we're pretty good at Riemann sums at this point, so we know that this is actually going to turn out to be a definite integral of 32,144x dx. All right, so now what we need to do is just talk about the bounds of integration. How much depth or how much water do we want to, in this case kerosene, I apologize, do we want to add up? Well, looking at where I labeled my x-axis, I want to integrate from 0 now to 1.5 because the tank's not entirely full, but this will represent all of the x values of kerosene pressing against that vertical plate. So our bounds of integration will be from 0 to 1.5 meters. All right, again, the setup is the hardest part because now you can see that our integration becomes pretty simple. We'll get 32,144 x squared over 2, evaluated from 0 to 1.5. And if you put all of that together, you should get 36,162 newtons, or approximately 3.6 times 10 to the 4 newtons, depending on whether you're a scientific notation person or not. So it's important to pay attention when you're looking at these problems on whether they're asking you for the pressure against a horizontal plate, like the bottom of the tank, in which case the pressure is uniform and nothing is changing, and you don't need any kind of Riemann sum to calculate that. Or if they're asking you for the pressure pressing against the edge of a plate here. Well, depth is a key component in that pressure, and so you have to take into account that that's changing, and that's why we need a situation like this. So that's the first problem we're going to look at for hydrostatic pressure and force.